Welcome back everyone. In this lecture we will continue to study functions. So, let me begin with one important exercise that actually characterizes injective functions. We already seen some characterization. So, this gives more characterization of injective functions. So, let us start with a map. F is from x to y. So, let us say this is a given map, and then we want to say that the following are equivalent. So, this I am not going to prove, I will leave it as exercise. The very first statement is that F is injective, one to one map. So, which is equivalent to say that when you take pairs of subsets of capital X, call it A and B. So, then F of A intersection B is equal to F of A intersection F of B, and this holds for all A B subsets of X. The third condition is that, so whenever you have A intersection B is empty, then look at its image F of A and F of B, their intersection also should be empty. So, for all pairs A B subset of X such that A intersection B is empty should give us F of A intersection F of B is again empty. So, like this we can actually come up with many characterization. Okay, I guess I have already proved that 1 and 2 are equivalent. I am leaving you to check 2 and 3 are equivalent. Okay, so some of these general criterions are actually helpful whenever you are actually trying to prove something about a map. So, in general if you think about it, proving some given map is injective or surjective, that actually requires some information about the map and where it is defined and so on. And in practice, like many problems that we encounter in mathematics can be actually stated as a map being injective or surjective. So, I am going to actually demonstrate that using some examples. So, in particularly I am going to prove that any given prime of the form 1 plus 4k that can be written as sum of two squares, that is a celebrated Fermat's Little theorem in number theory, which will be proved using sophisticated algebraic ideas in the later part of the course. But now what we will do, like we will actually give an ingenious proof of Don Jaeger that actually he kind of formulated the same fact in terms of being some map being involution. So, I will do that as an example of powerness of checking some function being injective or surjective, giving very strong mathematical facts. Anyway, so let us actually begin with first of all some examples of functions. So, if we take for example f to be defined to be a function from 0 1 to 0 1, and let us say it is given by f of x equal to x square. So, then this function, like one can ask whether it is a bijective function or not. So, it is easy to ask a question, but sometime depending upon where it is defined and so on, those information that we have to use in order to check something about the function. For example, if we are interested in checking anything about this function, then we have to use little bit of analysis. For example, what does it mean by injective? So, that means whenever we take images to be equal, then the pre-images must be equal. So, that means f of x, let us say, equal to f of y. So, that means x square equal to y square. Then here what we can do little bit of algebra. So, because x square equal to y square, we know how to solve in terms of x and y. So, then this becomes x square minus y square equal to 0, which is in particularly gives us that x plus y times x minus y is indeed 0. But now note that x and y comes from this 0 and 1. So, that means both x and y are positive real numbers. So, the order property of real numbers tells us that if this equation is true, then that would imply x minus y must be 0. That is because x is positive, y is positive. So, x plus y is positive. So, it is never 0. So, that means I can cancel out that and then get that x minus y is 0. That means x equal to y. So, this proves x is this function f is injective. But then if we want to talk about surjective of this function, then some more nature of this function is actually required. And if you will be actually studying some continuity property of functions in real valued functions in basic real analysis course. And so, in terms of that, you can see that this function is actually continuous function defined on this 0 1. So, now using intermediate property, because this interval 0 comma 1 is connected. So, using that one can actually check using intermediate value theorem that this map is onto. So, sometimes we need to use heavy machinery coming from algebra or analysis in order to check given map is injective or surjective. Anyway, so I just wanted to give you one example to discuss about this. So, one can also ask like simply whether one can come up with bijective functions from given two sets or not. Okay. In practice, like that actually kind of related with what is called cardinality of given set. Okay. If we want to say actually two sets are having same cardinality, so it makes sense to define that they have actually there is a bijective function from one set to another. Okay. So, I will discuss about cardinality later in this course, but that actually kind of motivates us to look for bijective functions from given set x to y. Okay. So, let us actually try to do some examples and then later we will discuss about cardinality. So, for example, one can take this interval bracket a b and then interval bracket 0 1. And if you think about it intuitively, it is clear that the interval bracket a b for any a b coming from R such that a less than b. So, the number of elements in the interval a b should be same as the number of elements in interval 0 comma 1. Okay. So, that means there should be bijection. So, I am saying that intuitively it is clear. So, but we need to write down bijection to make everything mathematically precise. So, that means we need to find a bijective function from this interval close 0 comma b to a comma b to close 0 comma 1. So, now if you think about it, so you have taken an interval a comma b and then the interval 0 comma 1 is indeed fixed. Now, depending upon the length of the interval which is b minus a, one can see that the size of this interval either like smaller than size 1 which is the size of this 0 1 or it is bigger than the size 0 1 size of 0 1. So, for example, a could be 100 and b could be 1000. In that case, we are getting really large interval. But then how do you actually scale it? So, if you think about it, you can take any large interval and then you can actually either you can squeeze it and then make it 0 1, and if you take a smaller very smaller interval, then you can stretch it and then make it 0 1. So, this scaling is actually gives us actually the bijection. So, if you want to put it in more mathematical term, you define a function x goes to. So, what I want to do is I want to map A to this 0 and then this B to this 1. So, that means I am doing is stretching. So, if you think about it, the way you do is, for example, if I take this linear equation x minus a. So, x goes to x minus a clearly sends a to 0, but the problem with b will go to b minus a. So, that means I have to kind of scale it so that it goes to 1. So, you scale it by 1 divided by b minus a, which is the length of the interval. Then it is clear that the map x goes to x minus a divided by b minus a maps a to 0 and then b to 1, and I will leave it as exercise, and then you check directly that this map is indeed bijective map. So, the exercise is that this map, let us call it small s, is a bijective map. Okay. So, let us actually prove one important result, which will be again and again used in at least basic algebra and analysis. So, if I start with a map which is defined from x to x on a same set, and assume that f composition f is indeed injective. Okay. So, you can call it as a lemma. So, if I start with a function f which is such that f composition f is injective, then that would imply that f is injective. For example, we defined involution to be f composition f being identity. So, that means f should be injective, okay, according to this lemma. So, now if you think about it, how one can prove. So, take two elements x y in capital X such that whose image is same under f. So, now we need to say that the pre-images x and y must be same. So, now once f of x is same as f of y, what I can do? I can apply f again. So, then f composition f of x is going to be f of x. So, which is going to be equal to f of y, which is f composition f of y. Okay. But now you know that f composition f is injective. So, that would imply that x is same as y, because you have taken two elements x and y such that f composition f of x is same as f composition f of y. So, but being f composition f is injective will imply that x equal to y. So, this proves that f is injective. Okay. As a corollary, you can get if f composition f is identity on x, that would imply f is injective. Not only that, you can also do this for any number of compositions. Suppose if you have a fixed k such that f composition f k times is identity, then that would imply again f is injective. Similar proof actually works. Maybe you can take it as exercise. Okay. So, now if you actually think about compositions, then you can easily see that the composition of functions, they are indeed satisfies what is called associativity law. So, we actually need this only for functions defined on same sets, but I have already told you to define composition of function. So, the codomain of f should be same as domain of g, then g composition f makes sense. Okay. So, suppose if you have three functions, let us say f, g, h are given to be 3 functions. So, let us say they are defined on sets, so that the composition of F composition, G composition, H makes sense. So, F composition, G composition, H. So, this makes sense. So, then what is the associativity law says? F composition, G composition, H is same as F composition, G composition, H. So, this is what associativity law actually gives us. Okay, so to make this work, let's actually write down the domains and codomains properly. So, first I want G composition H to make sense. So, then H, we want X composition, G composition of X, let us say it is applied on some small x, then we get F of G of H of X, that is what I get. Okay. So, that means the domain of this H, so the domain of H, which is let us say going to call it as some A to B. So, the domain should be the codomain should be the domain of G. So, the G is here, G to C. So, you start with X here, then H of X is here, then G of H of X is here in C. So, then you have this F, which is defined from C to D, which is F of G of H of X. Okay. So, the codomain of H should be the domain of G in order to make G composition H make sense. Okay. So, now by definition of F composition, G composition H, you can see that first we will be actually applying this G of, so what is the definition of this? This is F of G composition H of X. So, first we apply G composition H of X, and then on that we apply F, which is same as saying that F of G of H of X. Okay. So, now let us calculate what happens to the right hand side, F composition G composition H and applied on X. Then this is going to be F composition G of H of X, which is same as F of G of H of X. So, for any x in capital A, you have that F composition of G composition of H of X is same as F composition G composition H of X. So, that proves that whenever these functions or the composition of these functions are well defined, then the associativity law actually holds. But note that the commutativity law, that does not hold whenever your set is has at least 2 elements. Okay. Actually at least 3 elements. So, exercise is that suppose I have set X with the number of elements in, okay. So, let me write it as number of elements. So, the number of elements in X is at least 3. Okay. So, then we will be able to find functions f and g defined from x to x such that f composition g is different from g composition f. Okay. So, this is always true. So, that means commutativity between these composition is never happening, okay, but associativity is always there. Okay, so now let us look at some other interesting function that one can define on the sets and with its power sets. So, we already seen that Russell paradox actually talks about like how one should be careful about defining sets in terms of injective axioms. So, if you just take a collection of all sets, okay, such that set is not contained in itself, we just seen that it is not actually going to be a set. And the ideas that are used in that proof can be actually explored further, and then those ideas can be used in to prove that we cannot have actually surjective map from x to its power set x. Okay, first of all, let us try to understand what is really happening. Okay. So, given a set x, so we already seen what is the power set of x. So, power set of x is nothing but you collect all possible subsets of capital X, okay. That is what we call it as power set of x. And it is clear if at least you can see it in the finite case. Suppose x has fewer number of elements, okay. Let us say x has 3 elements, x1, x2 and x3, and it is not difficult to actually prove that power set of x will have exactly 2 power 3 elements, which is 8 number of elements. So, let me just write it down. So, the power set of x will have empty, the singletons and 2 sets and the 3 sets. Okay. So, you can see that totally there are 8 number of elements. But anyway, this example already demonstrate that if you start with a set, the power set of that set should be really must be having like a large number of elements, then the set that you started with. Okay. So, we want to put that in more mathematical language. Okay. So, later when I talk about cardinality, I will actually tell you like what it means by saying that a given set, the power set of that set is indeed having more number of elements than given set. But before that, let us actually prove that this Cantor's theorem, which tells us that there exists no surjective map from x to power set of x. So, if you think about it, intuitively it is clear that if you have a surjective map from set x to y, then it looks like, okay, at least in the finite case you will be able to convince yourself that the number of elements in x must be more than the number of elements in y, because surjectivity guarantees that for each element in y you will be able to get one pre-image in capital X. And since the definition of function does not allow one element map to different elements in y, so that indeed guarantees that you should have for each element at least you should be able to find one element in x. So, that tells that number of elements in capital X must be more than number of elements in y. Okay. So, since we are expecting that the power set should have more number of elements, so that means we should not be having any surjective map from x to power set of x. So, this is kind of intuitively very clear, and we want to actually prove that in more mathematical terms. So, this was first proved by Cantor, who actually invented the notion of infinity, various types of infinity. Okay. We will actually discuss about that later when I introduce cardinality. So, the Cantor theorem says there exists no surjective map from x to power set of x. Okay. So, when x is like even finite case, we will talk about finiteness later, you can see that this would never happen, because if x has some k number of elements, we will be able to prove the power set will have 2 power k number of elements, which is usually larger than k. For example, if we take x equal to empty, so then it is clear that power set has at least singleton empty. So, that is power set is singleton empty. So, it has one element, 2 power 0 element. Okay. So, let us actually prove this. So, usually there are many ways one can actually prove given statement in mathematics. For example, one can use what is called mathematical induction if there is an identity that is involving natural numbers and so on, and mathematical induction also can be used in various different places. But once if you can use mathematical induction, you can use and then prove the statement directly, and sometimes we can do direct computations and then prove identities or some results. That is the second way to do it. The third way is the most powerful way that is used lot in mathematics, both analysis, algebra and topology and so on, that is proof by contradiction. The proof by contradiction actually tells something like this. So, if you are interested in proving a statement, what do? You assume that that statement is not true. So, then try to actually work with that assumption and then you arrive at contradiction. Okay. So, then that contradiction tells you that the original assumption that you made is not correct. So, that means the original statement that you started with should be true. For example, this result is one of the examples, like great examples to demonstrate this proof by contradiction. So, here what we wanted to prove? We wanted to prove that there is no surjective map from x to power set of x. But on the contrary, what we will do? We will actually assume that there is a map and then we arrive to the contradiction. So, let us say we have a map x to power set of x, which is surjective. Okay. Suppose. So, then what happens? So, given any element here, okay, a subset of x, then there should be an element here x a such that it is mapped to that capital A. Okay. So, now what I can do? I can actually collect a subset of capital X, okay, let us call it B. So, this is those x in x such that x does not belong to f of x. Note that given x in x, f of x is indeed subset of capital X. So, since it is subset of capital X, I can talk about this x being an element of capital X, whether it is there in that subset f of x or not. So, this capital B is well defined. Okay. And you can use injective axioms to convince that it is indeed subset of capital X. So, now the question is this B that we define, that is those x in x such that x does not belong to f of x. Okay. So, this is subset of x. Okay. So, now since f is being surjective, that tells you that there exists x naught in capital X such that f of x naught is exactly equal to given by B. Okay. So, now the question is where is this x naught, whether it is in B or not. Okay. So, this is very similar to actually Russell paradox if you think about it. So, now we will be getting contradiction in either cases, that is the goal. So, if x not in B, then that would imply that by definition of B, that we have x naught not in f of x naught. Okay. But what is f of x naught, which is b? So, a contradiction. Okay. Similarly, the case 2, what it says, x naught is not in b. If x is not in b, that means x naught is not in f of x naught, because which is b. Then again by definition of b, we get x naught is in b, again a contradiction. Okay. So, this proves that such f should not exist. Okay. So, you can see that it is very similar to what we have done in the Russell paradox case, and that proof actually tells us that we cannot have any surjective map from x to power set of x. So, as an immediate corollary, we will see that later, that the cardinality of x will be smaller than, strictly less than the cardinality of p of x for any given set capital X. Okay, I will stop here, and we will continue with discussing about cardinality and so on from the next class. I will stop here. Thanks.